All right, welcome everyone. Today, well, it's another series test. So we got a few more to go here. Um, Today's, though, is the alternating series test. So this is a helpful one because it allows us to work with series that have some negative terms. So in this lesson, we're going to be seeing how to use this alternating series test to show that an alternating series is convergent. So first of all, what is an alternating series? Let's look at the definition. So it's a series that, well, it alternates between positive and negative terms. So something, just kind of like an example here. We'll look at a few examples. So a more general run here is the series given by the sum from n equals 1 to infinity of negative 1 raised to the n minus 1 times some positive bn terms here. So really what's giving us this alternating pattern are these expressions of the form negative 1 raised to some power n. So whether it's n minus 1, n, or n plus 1, this is what really gives us the alternating pattern. So we can see if we write out the first few terms here, the first term is b1, and we're assuming the b terms here are positive. So b1 is positive. Then when we go to the second, we have minus b2. So we're subtracting here. Or it's like we're subtracting. We have a negative term that we're adding in. Then plus b3, then minus b4. So we can see this power of negative 1 is giving us positive, negative, positive, negative. Gives us that alternating pattern. So, there's other ones out there. This isn't the only type expression that gives us an alternating pattern. So sometimes we see, the more common ones that give us alternating patterns are things like, well, this one, negative 1 raised to the n minus 1. But negative 1 raised to the n, negative 1 raised to the n plus 1, those kind of give us an alternating pattern. They switch between negative and positive, and we've looked at those before. Now there are other more creative versions that essentially do the same thing, give us alternating positive to negative, and those can be kind of cooked up with sine or cosine. But primarily we're going to be looking at these. All right. So we have a few examples here just to kind of see what these look like for more explicit examples. So here's one, the sum from n equals 1 to infinity of negative 1 raised to the power n. So that's going to also give us an alternating pattern over n. And if we write out the first few terms, we get negative 1 plus 1 half minus 1/3 plus 1/4 minus 1/5, and so on. And so we can see this, really it's this negative 1 raised to the power n that's giving us the alternating negative, positive pattern. Something similar for this other series. Sigma n equals 1 to infinity of negative 1 raised to the n minus 1 over n squared. And here it starts off positive, then goes to negative, positive, and so on. So it just alternates back and forth between positive and negative. All right, so, it helps to kind of picture these with the terms written out just to really emphasize the fact that they're alternating. But our eyes, if we see this written in sigma notation, we should really focus in on that negative 1 raised to power n. That's really going to give us the alternating pattern. All right, so let's look at the alternating series test, what we're actually going to be using here. So let's say we start with an alternating series, something similar to the one we just looked at, negative 1 raised to the n minus 1 times bn, where those bn terms are positive. So we're really emphasizing the fact that the only negatives that we're getting here are coming from this alternating piece. And what the alternating series test does is it says we really focus in on these bn terms. So the majority of our test here is we really separate off the kind of the non-alternating part. So the alternating part is this power of -1. We really look at everything else and we investigate two properties. So how do we investigate this? Well, we really separate off the non-alternating part. So we're going to separate off the power of -1 and just look at everything else. All right, so there's two conditions that need to be met for this alternating series test. So the first condition is that our sequence of Bn terms are decreasing. And that's what that first part says. So our Bn terms, what we've separated off from that alternating part, the Bn terms need to be a decreasing sequence. So explicitly, that means Bn plus 1 needs to be less than or equal to Bn for all n. So as we go further out into our sequence, the terms are getting smaller and smaller compared to the ones that have come before. So Bn plus 1 is smaller or equal to Bn. And this is true for all n. So it's a decreasing sequence. The other condition is that the limit of that sequence Bn, the limit of those Bn terms, has to go to 0. So these are the two conditions we're looking at, we're going to investigate. So Bn needs to be a decreasing sequence, and the limit of Bn has to go to 0. So there's two conditions here that need to be satisfied. And if those two conditions are satisfied, then the alternating series is convergent. So it's worth pointing out that this test cannot be used as is to show divergence. It can only be used to show that a series is convergent. So we can't use it to show divergence. So only that a series is convergent. All right. So we're going to see a few examples. Well, there's a couple other things to mention. And one of them is how do we show decreasing? Well, we can show it. There's a few ways to do this. We can just show it with inequalities, or we can kind of go back to a real variable function and use derivatives. So there's a few ways to show this. We could show that with inequalities. Or we could use derivatives to show that decreasing. So we know if we convert it to a real variable function, then the first derivative, when the first derivative is negative, that's when it tells us our function is decreasing. So we can either do it directly with inequalities, sometimes that's a little easier, or we can use functions and look at the derivative and see where the derivative is negative, and that can be sometimes a little bit easier. So it depends on how complicated the Bn terms are. All right, so just a few tips and warnings here. So we have our alternating series test. We had that inequality that Bn plus 1 must be less than or equal to Bn. It's a decreasing sequence. we can relax that condition a little bit, as usual. So we've seen this before. This doesn't have to happen directly at n equals 1, and then from then on. We can kind of relax that condition so that it eventually happens for all n. So if we go far enough out, there's some index number, capital N, where that inequality is true from then on. So if there's a couple terms at the beginning where the inequality isn't satisfied, that's okay. As long as we get to a point where it is satisfied then going forward. So that's the one just little notice there. The other notice here is that as it's written, the series test here involves -1 raised to the n minus 1. Really, this could be rewritten with any of those other kind of similar alternating pieces. So -1 to the n or -1 to the n plus 1, any of those, there's other ones too. So any of those type little gadgets here that give us an alternating positive, negative pattern, the alternating series test works for those as well. Now, one warning here is, why this test is helpful is that the integral and comparison tests that we've looked at so far, they actually cannot be used when investigating the convergence of an alternating series. And the reason is because those tests had a positive requirement. All of the terms needed to be positive for us to use those tests. So we're kind of expanding our scope here, and we're actually finding a series test that allows us to investigate the convergence or divergence of kind of a whole new group of series. So just a little warning there. So let's look at an example. Let's look at example 1. We're going to determine if this series is convergent or divergent. So it's the one we had written out at the beginning there. It's the sum from n equals 1 to infinity of -1 raised to the power n over n. And the first step that we want to do here is we want to kind of separate off that alternating piece. So we want to rewrite this. It's helpful to do it, not absolutely necessary, but it's usually helpful to conceptually to write this out. So we're going to write our sum, and then we're going to separate off that alternating piece. So we're going to write this as -1 raised to the power n times 1 over n. So we see the alternating piece. Right now it's kind of mixed together in this fraction. Let's break that apart. And doing that, really that's a helpful step. So this is kind of a simple example, but there's going to be more complicated series that we look at where this is going to be helpful. So we just want to separate off the -1 raised to the n minus 1, and that helps us identify what Bn is. So what is Bn here? Well, it's right here. So this is what we're going to be considering. This is what we're going to be investigating here, this 1 over n. All right, so what do we need to check? So there were two conditions that we needed to check for the alternating series test. We needed to check the limit of Bn as n goes to infinity. We need to see if that's equal to 0. And then we also needed to check that Bn plus 1 was less than or equal to Bn for all n, or sufficiently large n. So those were our two conditions we needed to check. And normally it's actually easier, or it's helpful to start with the limit first. And we'll see why in the next example. But usually it's helpful to start with this limit first, because if the limit's not equal to 0, then the alternating series test doesn't work. So this is normally a slightly easier one to show. So it's helpful to start with it. All right, so let's do that. So let's compute the limit. And we have a whole bunch of limit techniques. So we have a whole slew of limit techniques that we've looked at. We've seen how to compute the limit of a sequence. This is something we've done before. So we're just looking at those Bn terms. We've separated them off from that alternating piece. So we're just looking at, in this case, 1 over n. So let's investigate. We're going to do the limit of Bn as n goes to infinity. Let's actually fill in what Bn is in this case. So it's the 1 over n. And we know that's one of our c over infinity forms, so that is equal to 0. So check. That first condition is met. Good. All right, so we've shown the limit of our sequence actually is equal to 0. Now let's show that it's a decreasing sequence. So that's what we'll do next. And when we do this, it's helpful to kind of write out. We have to show that Bn plus 1 is less than or equal to Bn. So it's helpful to first write down explicitly the Bn plus 1 and the Bn terms. So write these down. So Bn plus 1, this might take a little, you got to be careful when you do this. So let's start with Bn. Bn is just the 1 over n there. And so when we write down Bn plus 1, we're going to look at our Bn formula. And again, kind of think of this like a function. So we're thinking of when we plug n into this function, we're getting 1 over n. So when we plug n plus 1 into our function, what do we get? Well, we're going to get 1 over n plus 1. So basically, wherever we see an n in our original formula here, we're replacing it with n plus 1. And so once we have our kind of our Bn plus 1 and our Bn written down, the next thing we want to do is use inequalities. Or maybe derivatives. Maybe that's a little bit easier. In this case, the inequalities is not too bad. So we'll do inequalities here. So you start with what you want, and you simplify it down until you get something that's clearly true. So let's start with what we want. We want Bn plus 1 to be less than or equal to Bn. So let's fill in what those terms actually are. 1 over n plus 1 is less than or equal to 1 over n. So if and only if. So this statement here is logically equivalent to 1 over n plus 1 being less than or equal to 1 over n. We don't technically know this yet. But here we get to a point where we can essentially multiply both sides by n. So we get n on the left. And then the n times 1 over n cancels on the right. And then we can multiply both sides by n plus 1. And so the n plus 1 cancels with the 1 over n plus 1 on the left, and then we're left with just an n plus 1 on the right. So it kind of cross-multiplied here. And we know we can do this here because n is greater than or equal to 1. And this is clearly true. This last statement is clearly true. The number n is definitely less than or equal to n plus 1 more. So this is clearly true, which means our starting inequality is clearly true. So check. bn plus 1. Since n is clearly less than or equal to n plus 1, that means bn plus 1 is less than or equal to bn. So both of these conditions are met. We can actually make our conclusion. So therefore, this series converges and we want to get into the habit of clearly writing out what test we're using. So we're using here the alternating series test. So let's write that. We're saying our series converges, and then we're explaining by the alternating series test. All right, there we go. So let's try another example. Example 2. So here we have another series. We want to see if it's convergent or divergent. And what is it? It's the sum from n equals 1 to infinity of negative 1 raised to the n plus 1 times 2n squared over 5n squared minus 3. So we immediately focus in and we see this alternating piece here. So we suspect alternating series test. So let's go through what we did in the last one. Let's separate this series. So we're going to separate out that alternating piece, the negative 1 raised to the n plus 1. And then let's write out what everything else is. So 2n squared over 5n squared minus 3. All right. So this is going to be our bn. That's what we're going to be investigating. So let's write out. What do we need to check? There's two things. First thing, we need to show that the limit of bn as n goes to infinity is equal to 0. And then we need to show that it's a decreasing sequence. bn plus 1 is less than or equal to bn. All right, so let's start with our limit. So let's show our limit. All right, so let's fill in what we know bn is. It's this 2n squared over 5n squared minus 3. And doing the limit as n goes to infinity. Now when we think about this, the top here has an n squared, so that's going to infinity. The bottom here, the denominator, also has an n squared, so the denominator here is also getting really large. So this is an indeterminate form. So there's a few ways we can do this. We can either convert this to a real variable function, so convert these to x's and then use L'Hopital's rule. Or we can just use our 1 over n trick, where we divide each term here in the numerator and denominator by the largest power of n in the denominator. So we identify the largest power of n, which is the n squared, and we're just going to divide everything by n squared. So essentially what we're doing here is we're multiplying everything by 1 over n squared. So that's one of our standard techniques for dealing with these types of indeterminate forms. So what do we get when we do that multiplication? Well, the n squared times the 1 over n squared, those cancel, and we're left with just a 2. The 5n squared multiplied with the 1n squared, the n squareds cancel, and we're left with just a 5. And then we also distribute to this negative 3, so we're going to have negative 3 over n squared. And so why this is helpful is because we know individually what these 1 over n and 1 over n squared terms are doing. Those are our c over infinity forms. They all go to 0. So we can actually calculate the limit of this numerically. So what do we end up with? Well, the constant 2 stays 2. The constant 5 stays 5. And then that minus 3 over n squared, that goes to 0. So this limit here is 2 over 5. And, well, we ran into trouble. we needed to show, in order to use the alternating series test, we needed to show that the limit of Bn was equal to 0, and it's clearly not. This is clearly not equal to 0. So this first condition doesn't work out. So what that means is we don't even have to go through and try and show that inequality. Doesn't matter at this point. So we don't even need to check this. Since the limit doesn't equal 0, we can't use the alternating series test. So that's why it's helpful to check the limit first, because it's normally a little bit easier, a little bit more straightforward to show. Sometimes these inequalities can get it takes a little bit more work. So kind of get the easier one done first. And in this case, we've shown that the limit doesn't equal 0, so we don't even need to show this inequality because it doesn't matter. So this is trouble. What are we going to do? Our alternating series test doesn't work. So since the limit of Bn does not equal 0, as n goes to infinity, we cannot use the alternating series test. And we already know with an alternating series, because there's some negative terms here, always do that once. There we go. We can't use the alternating series test. What else do we have? We have the integral test. We can't use that because we have some negatives. Can't use our comparison tests, either one, because we have some negatives here. So there's only one other option, and it turns out this other option always works in this case. So unfortunately, if the limit of Bn does not equal 0, the alternating series test just doesn't work. But instead, we can fall back to our test for divergence, and that kind of saves the day. So if you find that the limit of Bn does not equal 0, the alternating series test doesn't work, but then that's an immediate indication that the test for divergence actually would work. So if you find that this limit does not equal 0, then it's okay. You just have to then go and jump to the test for divergence. So let's see what this looks like. So since the limit of Bn, as n goes to infinity, is equal to the limit of, what was it, 2n squared over 5n squared minus 3, as n goes to infinity. And since that limit does not equal 0, if that we throw that alternating piece in, if we throw that alternating piece back in, the negative 1 raised to the n plus 1, what happens then is this 2n squared over 5n squared minus 3 is getting close to, what did we see, 2 over 5. So it was getting close to 2 over 5. But what this alternating piece is going to do is it's going to send some of the terms to close to positive 2 over 5, and then it's going to send the other terms to negative 2 over 5. So we're going to have this back and forth where some of the terms are getting closer to positive 2 over 5, and another set are getting closer to negative 2 over 5. So this limit does not exist. And so therefore, by the test for divergence, since the limit of an, which is just the limit of our original terms here, does not exist, the test for divergence says that our series must diverge. Since the limit of an does not exist, so this is an here. An is just everything that we originally started with. So since the limit of an does not exist, the test for divergence tells us then that the series sigma an must diverge. So this is how we handle the case where if the limit of bn does not equal 0, the alternating series test doesn't work, but then we can immediately go to the test for divergence, and that will give us an answer. So this is just another, this is just an example of what happens if, those conditions aren't met. All right. So let's just summarize that real quick. So this is a result that we'll see, and it's worth kind of just formally stating here. So if you're going along, and what happens if we have a series where the bn terms do not satisfy one or both of the conditions? Well, then the alternating series test cannot be used, but then, like we said, we can immediately go to the test for divergence. So this means either bn plus 1 is, you're going along and you're showing kind of the reverse of what we want. bn plus 1 is greater than bn. Or you're showing that the limit of bn does not equal 0. If you get either of those, then immediately you can go to the test for divergence. So why does this one, if the terms are increasing, well then these are positive. They're positive and increasing, and it means then that the limit would not equal 0. So if you see this, chances are then that the limit of bn does not equal 0. And you can just calculate that directly. So if either of those conditions are not met, most likely what's happening here is the limit of bn does not equal 0. And then, like we said, you can go and use the test for divergence. So the alternating series test wouldn't work in that case, but the test for divergence would. And that's because if the limit of bn, as n goes to infinity, does not equal 0, well then the limit of -1, with that alternating piece put in there, -1 raised to the n minus 1 times bn, that does not exist. So if the limit of bn does not equal 0, then when we put that alternating piece back in, it's going to send some of the terms to kind of positive, some of the terms to negative, and they're not going to get any closer to each other because this limit does not equal 0. So they're going to they're going to alternate kind of far away from each other, respectively. So the overall limit does not exist. All right, so this is just a worthwhile note here. Because as we saw in example 2, this sometimes happens. You'll be going along, looks like an alternating series. You want to go through and show the conditions. If one of the conditions or both of the conditions is not met, well then chances are test for divergence is where you want to go. All right, so we're going to stop there for today. We'll look at another example next time for an alternating series, just to get a little bit more practice. And then we have a few more series tests coming up on the horizon, so we're almost there. We've almost gotten through our test, but we got a few more coming. So we'll see you then. Bye-bye.